Hello students, let us today quickly discuss double-slit diffraction. So we already discussed that how the diffraction for a single slit looks like, and we saw that the intensity pattern was much different than what we saw in Young's double-slit experiment. But what happens when we combine these two? So suppose now I have a double-slit system, but this time we are looking into this system with the lenses of diffraction as well as of interference. We already know that if I have a double slit, then interference is supposed to happen. So the intensity distribution that we saw for two slits in interference was something like this. I was I0 cos phi by 2, and we saw those equal intensity distribution pattern and fringe width we calculated already. You are experts of that by now. So this was the expression for two slits having interference, but at that point in time this D that we considered was the distance between the two slits. So this was D. Okay, so AB and CD, we are taking them as two of my slits, and D is the distance between them. So D was the separation between the two slits, and in that point in time we considered that both these slits were just 2 points, 2 point sources through which the coherent light was passing through. But now, while considering diffraction of single slit, we already saw that if we consider that the width of the slit is not like a point anymore, but it is comparable to the wavelength of the system, then this kind of an intensity pattern occurs, where to avoid the confusion, I wrote the slit width as A. So this A is the width of the slits that we have. Okay, so in this scenario, if I consider the double slit system once again, where the two slits are not points but slits of a finite width of A, what should be the final intensity pattern that we see? Now, to very simply tell that, we can simply say that it will be a combination of both these effects, isn't it? So the resultant that we see now for the double slit diffraction should give me something like this: I equal to I0 cos square pi d sin theta by lambda. So this is the part that comes due to interference, okay, times sine of pi a sine theta by lambda, pi a sine theta by lambda whole square. So this is the part that comes into the picture, because of the diffraction that is occurring at each of these slits that we have. So this is the final intensity distribution, where this is the contribution due to interference and this is the contribution due to diffraction. Looking at the system like this, that means a combination of interference and diffraction is a very general way to solve these problems. So what you can assume is that, suppose these slits were just points and thus you considered just the interference. Once you calculated the interference, then you extrapolated your problem for a system where the slits were a little bit bigger, and you considered diffraction separately, and you just added the contribution of diffraction in terms of multiplication to the intensity. In the other way around, you can also think of it like this way, that suppose there was only a single slit and it was refracting light, and once you added another slit, interference came into the picture, and thus you added a contribution because of the interference phenomena that is happening here. So this is a very general way to deal with this problem. Now, not just by extrapolating, but by a simple calculation also, we can show that this will come into the picture. So for that, I want to teach you a very general method, and then we'll extend the problem for not just 2 slits but 3, 4, 5 in number of slits, and we'll see that what happens to the intensity distribution once you consider all these slits. So to consider that, let us consider first that suppose we know that diffraction for a single slit always occurs, and this is the expression for intensity for diffraction of a single slit. With this knowledge, we are considering interference, and now we are not considering that the slits are wide anymore. So the width of the slits are taken into account as the phenomena of diffraction. Okay. Now we are only concerned about the interference. Now we are already did the calculation for interference once, but this time I want to teach you a tool that works for not just 2 but many slits. So for that, let us consider 2 slits separated by a distance d, and this is the screen. Okay, and light is coming out of both the slits and they are falling on this point. I want to figure out what is the intensity at this point. So doing the same calculation that we did for Young's double slit, we will draw a perpendicular like this, and we'll see that what is the path difference that is coming into the picture. But this time I want you to take the equation of the waves a little bit in a little bit different way. So consider that the ray from slit 1, if we write down the equation of the wave, it looks like y is equal to real part of r e to the power I omega t. Okay, instead of considering cos omega t, I am considering real part of e to the power I omega t. You know that real part of e to the power I omega t will be cos omega t only. But we are considering this in terms of exponential so that we can extrapolate the problem in a much easier way to more than one slits. So this is y1. Similarly, the wave from slit number 2, this can be written as y2 is equal to real part of r e to the power I omega t plus phi. There will be a extra phase difference because of this path difference that came into the picture, right? So here this r, interestingly, what we have to consider here is that this r that I am writing here as amplitude is basically, this basically takes into account of this term as well. Okay, so finally when we replace r, we'll put not only the amplitude but also the diffraction term. So we will keep that in mind. Okay, so now let us look at this phi, and we know how to write down this phi. This is the phase difference that comes into the picture because of the path difference, and the path difference we know it is d sine theta. We already know this calculation, how to do that, right? So phi can be written as 2 pi by lambda d sine theta, right? Okay, so the resultant displacement y will be r e to the power I omega t plus r e to the power I omega t plus I phi. Okay, so real part of this is going to give me the resultant displacement. Now I take common of a few things, so it will be real part of r e to the power I omega t, and left inside is 1 plus e to the power I phi. Okay, so what is this? This I know as a sine alpha by alpha. This r we replace by this, considering the diffraction term. Okay, so this R includes the diffraction contribution. Now e to the power I omega t was there, okay, and we have 1 plus e to the power I phi. Fine. So next step, we consider the intensity. So the intensity is going to be a square of this, right? So I will be a square sine square alpha by alpha square for this, okay. Now this goes off because we are considering only the amplitude, the intensity, so this is the wave part, this will drop off. What about this? So for that, because we are considering I here, instead of taking I as a square, we will take it as y star y, like multiplying the, figuring out the amplitude, right? So if you do that, what do we get? We get 1 plus cos phi whole square plus sin phi whole square. Okay, this I guess you can do it. Okay, so just figure out what e to the power I phi is, put the values and figure out the amplitude of this. Okay, so once you arrive at this point from here, the next part is quite simple. We know we will replace everything in terms of cos, and we'll see that the final expression comes out as 4 cos square phi by 2. Okay, so this 4 cos square phi by 2 matches exactly what we have from our interference calculation of Young's double slit experiment, and this was the contribution for diffraction of single slit that we have taken into account, right? So this is the total intensity that we have in case of double slit diffraction, and this is the calculation. Now you will say that we already know this expression, right? We can calculate the same expression considering the Young's double slit experiment calculation that we have done before. But I introduced you to this particular way of calculating it in terms of e to the power I omega t and so on, so that now you can extend this problem and add another slit to it. So just consider there is one more slit. If there is one more slit, then there will be one more wave, right? And they will also meet here on this point, and there will be further path differences like this, and this again will be d sine theta. Okay, so why only 3? Add one more, 4 or 5 or 6, so you can go on adding n number of such slits together. Now what will change in this calculation if we add n number of slits? I will give you a hint, but this is an assignment. The hint, if you consider simply, then consecutively you will go on adding extra phase differences, because the path differences change, right? As you go on further and further down, more and more waves come into the picture with more and more path difference coming into the picture. So this wave, the first one and the second one, had a path difference of d sine theta. But the second one has the same path difference with the third one, right? So what is the difference between these two, first and third? It will be d sine theta plus d sine theta, right? So d sine theta plus d sine theta will give you 2d sine theta. Similarly, you will have, instead of just having y1 and y2, you will have a y3 where the phase difference will be a bit more with 2d sine theta here. You will have a y4 where there will be another path difference. So there you will have another extra path difference and extra phase difference. So you incorporate all these terms here. So consider y1, y2, y3 dot 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 yn, n slits. Okay. So this expression, instead of having just 2 terms, it will have n number of terms. N number of terms, but you can deal with the problem in the same way. You take common of r, you replace r by the diffraction term, and you forget about the diffraction there. We are only dealing with interference now, and inside you will have this kind of terms, n number of terms, where you will have this sum. Now how to deal with that sum? That is the assignment. You think about it. I guess you can do it because this will be a simple form of a GP. You solve it and figure out what will be the final intensity expression for n slits. So in a concrete way, I will write down the assignment and mail it to you, but this is more or less what I want you to do. Okay, so try this, have fun. This system with n slits is called a diffraction grating. Okay, and this particular thing in not only in optics but in several other fields, including X-ray diffraction, which is something that we are going to discuss in the next lecture. So try to figure out what is the intensity distribution. I will start from that expression in the next lecture. Okay, bye for now.